Okay. Hopefully everyone here can now see Qubit. And the first thing you want to do is set the directory where you're going to be working. So I believe it's going to be, let's see if that's the one. Yep. So we'll set our directory here. And we'll open up the journal file, which is the script that we've used to create our meshes. So the top level script is this mesh try3 journal file. And what you'll notice is in this journal file, the first thing we do is play back our geometry journal file. And so it's usually handy in Qubit to divide your meshing into several different journal files. So the geometry is kind of a basic one where you've defined all the curves, surfaces, and volumes within your model. And then you can separately mesh that using several different strategies. So we'll look at this geometry journal file. And here we are. So our strategy for this is to create several different points which will define curves. And then using those curves, we can in turn define surfaces that will allow us to mesh the geometry. We're also going to make use of the AprepRo, which is a scripting language within Qubit. It allows you to define variables, do looping, and different things like that. And one of the handy things you can do with this is you can say that you're going to use SI units, which makes it a lot easier to provide coordinates and things like that. So that's the first thing we'll do. We'll do that. Once you do that, you'll see that you have a list of variables down here within Qubit. So these are all things related to using SI units. Also, one of the first things you usually do is reset everything. This clears all of the history that you had in Qubit before so that you're not overwriting things. We'll go ahead and do that. And then it's frequently handy to turn off undo, which can prevent some problems. All right. So the first thing we're going to do, we're going to create some vertices, and we're going to remember, or we're going to store the values of some of the IDs. And the reason we do that is so that we can refer back to them later, either to create curves or to break curves at particular locations. So we're going to create our first vertex here, and then we're going to store the ID number of that within this variable right here. So here we go. We've created a single vertex, and if we look up here in our variables, we have, this is the ID number is 1 because it's the first vertex that we've created. Now we're going to create a sequence of vertices, and we're going to remember this one that's right here at the trench. And we're also going to remember the one that's right at the end of our list of vertices. So what we've done, we've created a set of vertices that run across our topography and bathymetry, and we've stored the ID numbers of 3 of these for future use. Once you've done that, what you can do is create a spline curve that passes through these. And so you tell it to use vertex number ID point topo west to ID point topo east. So that's the first vertex we created through the last vertex. We're going to create a spline curve that goes through all of those. So there's our spline curve. And that's our topography and bathymetry. The next thing we're going to do is create the top of our slab. And we do this in a similar way. We have our first vertex, which will store the ID number. We'll create several more. We'll store the one that's where the slab crosses the moho. And then we'll store a couple others. And then we'll create a spline curve that goes through all of these. So I'm going to create these vertices right here. Okay, so this is the top of our slab right here, defined by these vertices. And now we're going to create a spline curve that goes through those. Okay, there we go. Now we're going to do the same thing, but in this case, what we're going to do is take the points that we used to create our slab and just offset those to the east to create the bottom of our slab. So the way we do that is we copy this set of vertices, and then we're going to move them 120 kilometers to the east. So we'll do that. And there we have those. So that's that set of vertices. Now you can see we're going to need a couple more vertices to finish defining this along the rest of the edge there. So we'll create two more vertices and save the ID of the last one. So there we go. Now we can join those all together into another spline curve. And that's the bottom of our slab right there. So now we need to define the top of our mantle. And so we already have, I believe, a point over here that will help define it. But we need to get it along the western edge. So we'll define a vertex to do that right here. So now we've created this point here, and then we'll define the bottom of the crust there. So that'll be the continental moho. So there we go. Now we have this curve. And then to finish up, we have to define the remainder of the margins so that we can close the whole thing up into surfaces. So we're going to create, this will be the eastern side. There we have that. So now we have points that cover all of the extremities of our mesh here. So now we can just make curves that join those together. Okay, so now we've defined all the curves that we need, but what we need to do is to divide these up into separate surfaces. For instance, we need a region here that's the continental moho, or well, that's the continental crust. We need the continental mantle here. So we need to divide these curves, break them apart so that we can define each surface in terms of a connected set of curves. So that's what we're doing here. So the first one we're going to do, we're going to take the topography and bathymetry, and we're going to break it where it crosses the slab top curve. So that's meaning we're going to break it right there. So, okay, now you can see what we've done. We've broken that curve into two sections. We're going to break the rest of these curves. We're going to break the slab top curve the western edge, the bottom edge, and the eastern edge, so that they can, so that each surface will have a set of bounding curves. Okay, so now we've broken all of these. You can see all of these curves are broken now. Once you've done that, then you can start creating surfaces using the bounding curves. So you do that, creating a surface by a set of bounding curves. So the first one we'll do is the continental crust, which is bounded by topography and bathymetry, the western edge, the continental moho, and the slab top at A. What you'll notice is sometimes when you break these curves, well, always actually, you'll end up, the original name of this curve was slab top. When you break it, it'll then give you two new curves. One will have the original name, and the other will be slab top at A. And if you keep breaking them, you'll have parts that are called at B, etc. So this is the first one we'll do. Okay, so now we've created our first surface, which is bounded by these curves. We're going to do the same thing for the remainder of these surfaces. Some of them will be bounded by as few as 3 curves, and some will have as many as, let's see, 1, 2, 3, 4, 5, 6. So we'll do that. So now we've created all of our surface. You'll notice that sometimes the geometry looks a little strange, but it has actually been done correctly. That's just an artifact of the way that Qubit displays things. So now, we don't need these vertices anymore since we now have all of the surfaces that we need to define our model. So we'll first delete all of the vertices. So there we go. And then what we're going to do, an imprint operation within Qubit lets bodies on one side of a curve or surface know that there are other bodies on the other side, so that they're aware of each other. So typically what you do, you first imprint things so that they know what's there, and then you merge. And what that does, that reduces duplicate surfaces and edges, things like that. So first we'll imprint. Okay. Now everything on one side of a curve knows about things on the other side. And then we'll merge them together. Okay. So when we did that, it merged together 4 curves. All right, then to be able to split our curves, we're going to have to stitch everything together into a single volume. So that's what this command is right here. Okay, now we see we have our single volume. I'm going to set this so that I can, let's see, I want to be able to select, surfaces. So I can now show the different surfaces within our volume. Then what we're going to do, this is so that we can do our discretization. We're going to break parts of curves so that we can apply different discretization schemes along different parts of the boundaries. So the first thing we're going to do is split the top of our slab 80 kilometers from the end. So we're going to take that curve and split it 80 kilometers from its end right there. See that? Okay. Now, if we look, you'll see that that curve has two pieces. This part that we've split from this part over here. We're going to do a similar thing with a few others. We're going to do the same thing with topography and bathymetry, and then we're going to split the slab bottom 2 times. Okay, so we've split all of those. We have that, that. So now we're finished actually defining our geometry. We've come to the end of this. So now we can go back to where we do the meshing. And the meshing includes defining the discretization that you're going to use. So first of all, we're going to mesh the whole thing using triangles. So that's this part here where we'll say surface all scheme tri-mesh. And then these 2 commands have to do with the discretization size. We're going to apply a default scheme to all curves, and then we're going to take away any sizing function information because we're going to redefine all of the sizing information. So we'll just do that. Okay. Now we're going to use apropos again, and we're going to define our default cell size to be 8 kilometers here. Now, with some of our discretizations, we'll just apply a constant cell size, but with some of the others, we'll use what's called a bias curve. And what that does, it means that you start with, say, your minimum cell size, and then you increase by a bias factor, going from the smallest to the largest. So you would, say, have a particular cell size right here near the edge, and then using our bias factor, each cell along here will increase its size until you get to the end of the curve. So first of all, we'll define these factors within apropos. And then we're going to set our constant cell size along the slab top at A, along this topography curve, and along slab bottom at C. We can see what that looks like once we've done it. You can use it using the preview command. You can see it. We'll do preview mesh volume all. You'll see that what we've done is define our constant cell size along this section, and this section. Now we're going to use the bias curves for the rest of it. And so what you do is you tell it what the finest bias size is. You give it our bias factor, which we've chosen as 1.2. And you tell it what the starting vertex is. So this is for topography at B. So that's this curve. And if we want to see what that looks like, it's this curve. So to tell the starting vertex, we can just look over here. There, that's the one that we want, which is vertex 75. So we'll go back, do that. So now if we preview again, we'll see what we've done. We've defined mesh size that increases as we move towards the edge. Then we're going to do that with the remainder of these curves. Oops. Okay, and then if we do So that's what we've done so far. We come back, and then we're going to use a constant mesh size on the mesh boundaries. So we just say 50 kilometer mesh size along the boundaries. So there we go. And then there we go. So now all we have to do is mesh it up. And what you'll notice, you can go over here if you want to see what sort of quality you have for your mesh. We usually like to use the condition number to evaluate the quality of the mesh. You can see what you've got. And so you can see that it goes from 1 to 2.65, which is not too bad. Usually a value of 2 is a pretty good mesh. We can improve that a little bit by smoothing the mesh. And we use a particular scheme, which is the condition number scheme, to tell it what its target value is and how much CPU time will allow it to use. That's in minutes. Then let's do that. So it didn't do much, so we'll look again and see if it improved things much. Okay, it didn't change the values much, but what it probably did is moved more of these cells into the good range. And then finally, the last thing we're going to do is create our boundary conditions. So we'll just look quickly at that. So for pilot, we need to have material blocks that are groups of elements or cells that we will apply all of the same properties to. And so you apply blocks to different surfaces, or in 3D, it would be different volumes. So we're going to say block 1 is going to be the continental crust, which is this right here. So we do that. So now what we've done, we've created a number of different blocks, and we've given them names. So we have our continental crust, which is block number 1. This ID number is important to use in pilot. There's our continental mantle, our oceanic crust, and our oceanic mantle. So that's what we need for our materials within pilot. To apply boundary conditions, we need what's called node sets. So the blocks are sets of elements. The node sets are sets of nodes. So what we do when we're defining a node set, you first use a group because you can do logical operations on a group. And then once you're happy with the nodes that are in the group, then you can use those to define your node set. So we'll first define one for the coseismic part of the fault. So we'll add nodes that are within these different curves. One is slab top at A, one is slab top at D. So what you'll see you've created is a group here, which is this set of nodes right here. And that's contained within this curve and within this curve. Slab top at A, slab top at D. So that's all that we need for that group. So once we've defined the group, we'll say, okay, node set 20 is going to be group fault coseismic, which is the name we gave this group. And then once we do that, we'll give this node set a name. And we can use this name within pilot. So there we go. Now we've created a node set called fault coseismic, which is this set of nodes right here. So we just do similar things for the rest of our surfaces, or for the rest of our boundaries of interest. We have it for the slab top and for the slab bottom. So this will be all of our things that are on faults. These are our node sets now. This is the entire slab top. This is the entire slab bottom. Now we also need all of our external boundaries. We saved the nodes that represent topography and bathymetry because that is going to be our ground surface, and we want to separately save all of them to be able to look at the displacements there. So we'll define that as a node set. So we've done that. And then we need node sets for every boundary where we want to apply boundary conditions. So here's our western boundary. Oops. Eastern boundary, mantle, and then the bottom boundary. And finally, mantle. So now these are all of our node sets that we have. Ground surface, western boundary, eastern boundary. You can see that over here. We have, we have two sections of that, the top and the bottom part. There's the this part of the bottom boundary, the remainder of the bottom boundary, and then the coseismic part of the fault, and the remainder of it. So once we've done all that, that's it as far as defining the boundary conditions. And then the last thing you have to do is just export your Exodus file, which is done right here. It's a two-dimensional mesh, and we'll tell it to overwrite any existing Exodus files with this name. So now we've created that. So that went a little over time.
Charles, we have a question from Lindsay. Can you go back to the boundary condition file?
Okay.
Journal file?
Let's see.
So the question is about specifying the node set number in the journal file. And so that node set, like node set 12, node set 13, node set 14, that's specified by the user. So you can pick whatever node set scheme you want. You can pick 1 through n, or you can pick like your faults to be 10 through whatever, and then your boundaries to be like 100 through something. Those are used. We used in Pilot. We've switched to using, rather than using the node set number, which is still available, but we switched to using the node set name because it tends to be more meaningful.
I believe for Green's functions, you still need the node set ID number. Isn't that correct?
No, that's the fault ID.
What? Oh, the fault ID. Okay. Okay, so you'll see that these things on the fault, we've just, I think, gotten in the habit of defining all the fault node set numbers to be higher than the regular boundary condition node sets. It's just kind of tradition. Okay. Any more questions about that?
We have another question here.
Okay. Is this about the...
So there's another question about the apropos commands. And so, yes, if you look at the apropos commands, they start with a comment character.
Right here.
And so it goes comment character, open, curly brace. And so it's the open and close curly braces starting with a comment character are your apropos commands. I have no idea why they decided to start with the comment character, but that's just the way the Qubit developers decided to do it.
It is a bit confusing because at first glance they look like comments. Okay. Shall I go ahead and get started on the 3D meshing? Because what I'll try and do is get through all of these, and then if we have any more questions about either an individual one or general ones, we can do that at the end, hopefully. So I'll go ahead and so now.
So we had another question regarding the accuracy of the geometry displayed within Qubit. And if you look at the mesh,